Okay, okay. So let me start by thanking to Thomas and other organizers for they enabled me to give this talk here. Well, emergent gravity is a very wide concept and it's a very wide title. There are many different versions, and today I'll talk about a different take on this topic. So let me start with a summary, so that because my time is limited. So in effective quantum field theories with a UV cutoff, let's say lambda, all gauge bosons acquire masses in proportion to lambda. Gauge symmetry is broken explicitly, can be restored by invoking a kind of Higgs mechanism, as we did usually with the electroweak bosons. The anticipated Higgs field must break Poincaré symmetry since the cutoff itself is breaking Poincaré symmetry. The Higgs field can be linked to curvature as they both break the Poincaré symmetry. And gravity can emerge then holographically as a completion of the flat space-time effective quantum field theory. This is the summary of my discussion. And one last point, proper emergence of gravity brings in a plethora of new particles that do not have to couple the standard model particles, which is a very important thing because there is always a particle physics aspect of this, all we are doing, and so I will comment at the end on the particle physics aspect. Let me start with a simple summary of, let's say, the Sakharov's-induced gravity, which is a very typical starting model. In Sakharov's setup, we start with a flat space-time quantum field theory, but we assume that loops have curved metric. Then we compute loops and we obtain an effective action of this form. And this action, once you identify Newton's constant as the coefficient of the scalar curvature, you end up with a Planckian vacuum energy, Planckian scalar masses, and Planckian gauge boson masses. This is the problem with the emergent gravity picture of Sakharov, which is a very brilliant idea. It is known as induced gravity, but actually it's an emergent gravity deep down. And the question is very simple. Can gravity emerge in a way alleviating these problems? Well, it is a very hard problem, but let's start over from the flat space effective action. Just flat space, okay? We have these quartic contribution, and let's look at only the power law part. Quartic part, scalar masses and gauge boson part. We can compute these things actually. Eta is the flat metric. This CO is proportional to the number difference between bosons and fermions. CM squared summation gives you super trace M squared in the theory, whatever masses you have in your theory. You can compute even C5, for example, for Higgs boson, it is proportional to top part, you have a coupling squared. And you can compute even the gauge boson sector, CV coefficients for each gauge group. And these are the just typical numbers proportional to gauge coupling squared. And this has been, now what we can do is that we may restore gauge symmetries by invoking some sort of Higgs mechanism. I mean, this is the standard thing we approach to massive gauge bosons. This is something we have learned while we were trying to understand standard model and the gauge theories in general. So let's look at first the gauge boson mass term. It is we can write it like over there, like this, standard thing. Let me regularize this thing. I will take this thing to a curved space-time. In flat space, I introduce this kinetic structure, IV and IV tilde. They are identical terms, just by parts, by parts of each other, by parts integral of each other. In flat space-time, IV and IV tilde difference is 0. In curved space-time, it's proportional to Ricci tensor or the Levi-Civita connection, and therefore in flat space-time you can regularize gauge boson mass action with this term, changing nothing, but in a curved space-time you make this addition to the term. And then we can proceed with this setup. Let's compare with the physical gauge boson mass. This is the gauge boson mass action. This is our anomalous mass term coming from loops. On the left, MV squared breaks gauge symmetries. On the right, lambda squared and curvature both breaks gauge symmetries. But Poincaré breaking is not possible with the gauge boson mass squared. but lambda square breaks Poincaré symmetry as we have seen. And this is expected because lambda is cut off and R is curvature, it's already seen. And let's go ahead with this comparison. Now we want to restore gauge symmetry. On the left, we know this, we know the Higgs mechanism as usual. We introduce a spurion phi, and on the right, we introduce a spurion sigma, let's say. On the left, we obtain this usual mass term, the spurion field. On the right, we obtain this structure. On the left, we have this spurion, it can be generalized to Higgs field as a dynamical field. It gives us this kinetic term for the scalars, and gauge symmetry is restored in this structure. On the right, we don't know what to do, because we don't know what to use for sigma. It is unclear, because sigma corresponds to a Poincaré breaking field, quantity lambda squared, and we need to understand that. To this point, so question is what is sigma? And it cannot be identified because it should break Poincaré symmetry. And it is possible that it will be related to space-time curvature. At this point, Frogat and Nielsen published a paper long ago, and they found that without assuming any symmetries or conservation laws, in a general quantum field theory, absence of translational invariance can be attributed to the curvature of the space-time. And there is indeed a link between cutoff and curvature, and this cutoff tells us that there is a kind of Poincaré affinity between the two structures. Let's continue. And with this picture, having this picture, now we can complete this picture by identifying spurion with the affine curvature, because when the metric is flat, I should have still curvature corresponding to this lambda squared term. So it could be a affine curvature, or I should have what we call Palatini gravity. We can call this symmetry-driven Palatini gravity as a short SPG, and now we include non-gauge sectors under this transformation to obtain this total action. In this action, I can write down equation of motion for affine connection gamma, and it turns out to be a very simple thing actually. It is this thing, gradient of Q alpha beta should be 0, Q alpha beta is this tensor, and Newton's constant is found to be just super trace m squared. And now we can solve for a connection. Indeed, we can easily integrate connection to have this form, and enormity of Planck's scale gives us that gamma lambda alpha beta equals this term plus this green part. Curvature equals the usual metrical curvature plus this green part. And once we integrate these, we find that, for example, gauge boson mass goes away and gauge symmetries get restored. And for example, general relativity emerges from this coefficient term. Yes, quadratic sensitivity of the scalar masses gives rise to curvature scalar field coupling. And quadratic curvature part in the affine Palatini gravity gives rise to this quadratic UV quadratic curvature term, as you see. And therefore, we have an emergence of general relativity from metric affine gravity or Palatini gravity, however you call it. Let's summarize. Just we made these replacements. Just this Higgs potential. There is gauge symmetry is broken in the minimum, and gauge symmetry is exact at the maximum. Let's look at the affine curvature mechanism on the right. We made these replacements, and we have this action this time. Not the potential energy, but symmetry-driven Palatini gravity action. We start with a point where curvature equals lambda squared G mu, but under the dynamical equations, it runs down. It comes to this point where affine curvature equals metrical curvature. Planck scale takes this value, and connection equals the metrical connection. As you see, This minimum corresponds to massless vector boson. But this minimum corresponds to massive vector boson. So these two things are opposite to each other. It is in this sense that affine dynamics in affine space leads us to the restoration of the gauge symmetries. Gauge symmetries get restored under this evolution. So indeed we can compare these two. For example, maximum energy is massless mu. Here, non-extrema of this SPG action, Palatini action, is the starting point of this theory, where gauge bosons have an anomalous loop-induced mass. On the other hand, minimum of the energy, potential energy, here corresponds to broken gauge symmetry, that is massive mu, the observed mu, like W boson or Z boson, whatever. And here we have extremum of the Palatini action corresponding to massless vector boson. And this corresponds to general relativity, dynamically. System generates general relativity dynamically from the Palatini dynamics. If I am to summarize for you, there is this, the total action involves quantum field theory part and general relativity part. Quantum field theory part is this blue part, and general relativity part is the red part. We have here a quantum field theory with dimensional regularization in the classical curve background geometry. Loop corrections are computed in flat space-time with only metal loops. Here we have R plus R squared gravity with non-minimal couplings to scalars. Although the GN remain the involving derivatives of the fields, the bosonic fields, and they have loop-induced coefficients computed in the flat space-time. If you need to give a name, this is a symmetry restoring emergent gravity, and I call it just simply emergent gravity for simplicity. Let's look at holography of the structure. Actually, in the flat space-time, we have this vacuum energy density, lambda to 4 square terms. This corresponds in curved space-time to this structure, R squared R and pi delta phi R. And as you see explicitly, actually, what happens is that the affine dynamics, which started with the, I'm sorry, just here, okay, affine dynamics, which started with this initial condition and ended up in this final condition, did the following. It took actually the lambda to affine curvature, and its evolution gave us to metrical curvature, such that metrical curvature, space-time curvature, acts as actually the IR limit or IR scale of the theory. From this holographic structure, we can read of this easily. And here, of course, only this part is holographic. The other parts are not obeying the holographic rule. But these models are frequently used in cosmology in understanding dark energy, in modeling dark energy. People use such models. So let me finish with my predictions of the emergent gravity. Let me summarize. New massive particles are a must. They must exist for Newton's constant to arise to take the right value. Neutrinos must be Dirac. They cannot be Majorana particles, as otherwise the Higgs sector would be destabilized. Black hole shadow, photon radius, and quasi-periodic oscillations show some distinctive features. I mean, you can distinguish this type of emergent gravity from some others by using this kind of observations or analysis. We have analyzed actually a bunch of stuff under these event horizon telescope observations. Dark matter must couple with a strength mx squared over m dark matter squared for not to destabilize the Higgs sector again, which is a very important constraint. Okay, I'm almost done. Thank you. Higgs curvature coupling is about 10% in the standard model. We can compute it. It is something like 8%. So then, if you observe that Higgs curvature coupling is, let's say, is not 8% or is something like, let's say, 15%, you can make sure that your Higgs boson is coupling to new particles in the theory. There are new particles to which our Higgs boson is coupling. It is in this sense, it's a direct conclusive thing by observations. Detection of new particles can wait for high luminosity LHC. I mean, in this approach, new particles should couple weakly or feebly to the standard model particles. This means that at the LHC, we can hardly see any new particle. They are all very weakly coupled, and we have to wait for high luminosity colliders to be able to see such weakly coupled particles. Also, we can say that this can be valid also for lighter particles around the electronic scale, of course. Pure Einstein gravity is attained if bosons and fermions are equal in number. Indeed, if in the nature number of bosons are equal to number of fermions, then you obtain exact Einstein gravity without R² contribution, which is normally not possible to predict because general covariance allows you to add any curvature invariant in the theory. Cosmic inflation is expected to be Starobinsky type because the R² term is able to induce cosmic inflation consistently. This has been found by a collaborator of mine. I mean, we are working on this model. We are trying to explore it in different limits, in different setups with different collaborators. I thank you, all my collaborators. I have done all these with them. Thank you very much for that.
Thank you. We have time for maybe two questions.
Yes.
So I think that the question one has to ask is what are these particles that you expect? And when you say that bosons have to be equal to fermions, you mean the number of degrees of freedom have to match, like in SUSY?
Yeah, number of degrees have to match.
Just like in SUSY.
Like in SUSY, but there is no SUSY structure. No need to SUSY-like couplings or structure. But if they are equal in numbers, then what happens is that your particle correction is
But you
zero.
actually make super multiplets like in SUSY.
Yeah. You don't have to put it in super multiplet. All you need is equality of the bosonic and fermionic degrees of freedom.
And these are
But of course, supersymmetric theories are in this class. Yeah, I understand. Yeah. I imagine that there are new particles, new massive particles. These particles could be at the electroweak scale. They can weigh a little bit higher. It depends on the spectrum. I am not able to specify that spectrum, but I know that they exist. And I know that they do not have to couple to me.
So I mean, if they find some SUSY particle, you will be happy. That's right.
Yeah, very happy. I'll be very happy. At the electronic scale, if they find a SUSY particle, they say scalar top part, then I'll be very happy. Yeah, that's.
Good luck.
I hope.
Any quick question? Otherwise we have to continue. Okay, let's thank the speaker again.